Hi, I'm Dan Groninger. I'm product engineer for the Mentor instrument platform, and I'd like to tell you about our new conductivity measurement feature for the Mentor EM today. So, first of all, one of the most important things in conductivity testing is temperature. Temperature variations can do a lot to impact the accuracy of your measurement. So it's always a good idea with any conductivity test to allow your probe, your standard, and your material under test to come as much as possible to the same temperature. So sometimes this is difficult in a maintenance hangar or other outdoor locations, but as much as possible, a little bit ahead of starting your test, take your instrument, your standards, your probe, start up your conductivity workflow, and allow everything to settle for a couple of minutes. So we've really optimized the conductivity feature on the Mentor for comparative or relative conductivity measurements. When properly calibrated, the Mentor provides accuracy similar to or better than the AutoSigma 3000. But we've really optimized this workflow for the major steps in a relative conductivity test. That is, first step is to calibrate against a known standard. The second step, as spelled out in the number of inspection procedures, is to acquire a number of measurements from known good areas of the product under test. And the third step then is to go take measurements of suspect areas, comparing those against the averages. So I'll walk you through how that all works on the Mentor. Step one, when you start the conductivity workflow, you'll see some information about the steps of a conductivity test, and you'll have an opportunity to read up on some of the things that can impact the accuracy. And the first thing you see is the calibration standards values. So you'll have a set of calibration standards similar to this. You'll have a high and a low value standard. In our case, the standards are clearly marked at 58.81 and 8.5% IACS. So we can initiate a calibration by touching the caliper button near the bottom of the screen, and the instrument will coach us through the steps of the calibration. So the first step is to hold the probe in air, then you place it on the high standard, then you place it on the low standard. And the instrument will step you through each step of the process. We see there we have a good calibration. Now we can advance to the next panel of the workflow. Here we have a number of areas giving different pieces of information about the conductivity test. So in the upper left-hand corner is the raw conductivity number. Across the top there's a graphical representation, and it'll make more sense in a second, that shows the measurement, the conductivity measurements relative to the average that we've gathered. One factor that can really impact a conductivity measurement is coating thickness, paint, or other coatings on the material under test. Just like the AutoSigma, the Mentor can compensate for varying coating thicknesses. With a larger diameter probe, up to 20 thousandths of an inch of coating is okay. On the smaller diameter probe, up to 10 thousandths of an inch is acceptable. So we have some features here to provide some alarms and cautions when the coating thickness drifts out of acceptable range. In a similar vein, temperature has a large impact on conductivity. When we calibrate the instrument, the calibration temperature is recorded. We will show an alarm range of plus and minus 5 degrees Celsius from that calibration temperature, and we will compensate the conductivity readings anywhere from 0 degrees Celsius to above 40 degrees Celsius. If you get more than 5 to 10 degrees away from the calibration temperature, your accuracy may be impacted a bit, but it still gives quite acceptable results for most purposes. So we've done our calibration. If we go back and check the standard again, we have a standard value of 58.8. That was showing 58.6, well within the limits that we've set. So the next step would be, once we've calibrated the instrument, to go to our material under test. In this case, I have a large section of aluminum airplane here. So we'll call this our known good area of the airplane. So our next step that we would do is collect some samples for average. So we provided a feature here to do that. In the old days, you would have grabbed a pad of paper and a pencil, taken a number of readings with the auto sigma, jotted those on the paper, dug out a calculator and done an average, or just kind of winged it. But here we provided a feature for recording a number of samples. The instrument's telling me put it on the metal. And there's our first point, 38.95. So take another point, 39.01. Third point, 38.96. So we're varying right around 0.1% IACS, 0.05% IACS. So when we're done collecting our points for average, we collected 4 points there. The inspection procedures in this area vary. One manufacturer calls for a minimum of 4 points. Another manufacturer just says take several. You can set a threshold for that when you design the workflow. In this case, I've made it the requirement that we take at least 4 points for the average. So when we accepted the average, in the graphical view at the top, we centered the view, the graph, on the average point that we measured. And we set alarm thresholds at plus and minus, in this case, 2.5% IACS from that average. One manufacturer requires a 1% IACS, plus or minus 1%. The other 2.5%. In this case, we went with 2.5. So now if I take readings back in my known good area of the material again, you'll notice with each reading, the caret on the graphical view moves back and forth to reflect where that reading falls with respect to the average. And you'll notice a number down at the bottom that's changing, and we call that our delta value, or the deviation of the current reading from the average. So, this material is pretty consistent in this area. We're varying about 0.1% IACS. So now our test is to examine larger areas of the airplane and look for areas, maybe we suspect a lightning strike caused some heat damage to the plane. So what we'll do is begin to inspect in the area that we believe may have been affected. And as we start taking readings in those areas, there's a reading that deviates quite a bit in conductivity from our known good material. So our known good material is showing about 38, 39% IACS. When I come over here to some heat damaged material, it's at 43% IACS. So now we can walk away and take readings in that area, and you see that the gradient can be quite sharp between heat affected material and good material. So that's the basics of the test. One other thing to keep in mind when doing the conductivity test is that the structure of the materials can have a tremendous impact on the test as well. This particular piece of aircraft is actually a very complex structure. In addition to just the materials themselves, you'll notice that the area where I define known good is on a different sheet. I've got a lap joint right here. If I go below the lap joint, there's actually a different material on the lower panel than there is on the upper, slightly different conductivity. And this upper panel is made up of a sandwich material. There's actually at least 3 sheets of aluminum bonded together to make this upper panel. The sheet of aluminum in the center has a considerably different conductivity than the sheet of aluminum on the surface. The Mentor instrument is capable of taking conductivity measurements at 5 different frequencies. And as we go up in frequency, we begin to have a larger impact on our conductivity measurement from the panel on the surface. At the lower frequency, at 60 kilohertz, we're able to penetrate into the middle layer of material. It has a lower conductivity. The upper layer is actually a higher conductivity material. So we have to be careful when we're collecting our average points to pick an area of the aircraft that is similar in construction and materials to the area that we're going to inspect for damage. So one of the things that the Mentor can compensate for when taking the measurements is thickness of various coatings. Most of the articles that you're likely to encounter in the field are going to have a paint layer on them. And the paint layer, as long as it is not conductive, so if you have metal flake paint, that can have an impact. But if you have just a basic non-conductive paint, the Mentor is capable of measuring the thickness of the paint layer as well as compensating the conductivity measurement. So where we took our average reading, we were getting about a 32% IACS reading, give or take. I have a yellow plastic shim here that is 20 mils thick. And you'll notice the instrument now gives me a reading of 0.019 inches. And my conductivity reading has been compensated for that coating. Here's a 10 mil shim and a 5 mil. So the larger of the two conductivity probes can compensate for accurately for as much as 20 mils of material. So if we stack this up, go to 30 mils total of coating, you notice the conductivity reading starts to develop some error, and the coating thickness graphical measurement has alarmed to indicate that you've gone out of an acceptable range for measurement. So your measurements may still be useful, but just know that your accuracy may be impacted a little bit. So aside from coating, the other factor that has a major impact on accuracy is changing temperature. And as long as the probe is allowed to match the temperature of the material, you will still get an accurate reading. We compensate for, we say you'll get your best accuracy within 5 degrees Celsius of the calibration temperature, but we will in fact give you a warning when you've drifted out of that, but we'll still produce accurate measurements across the entire range of 0 degrees to 40 degrees that we qualify this test for. So as a demonstration of that, we'll heat up our piece of aluminum here. Our airplane is at roughly 26 degrees Celsius right now. You can see the temperature's displayed and is changing. We'll heat this thing up. And we'll take a break from filming for a minute because this isn't very exciting to watch. This is Okay, so coming back, we've used a heat gun. We've raised the temperature of this panel considerably. As I put the probe down on the material, you'll see the thermometer reading on the instrument begin to climb rapidly. We post a warning once we've gone outside the 5 degrees C range. We show a yellow thermometer now to alert to the fact that the temperature is considerably different than our calibration temperature. But you notice our reading, our relative conductivity reading, really hasn't changed very much. So one hint, when you have an environment where the temperature of the probe may be changing rapidly due to changes in temperature of the material, rather than keeping the probe in continuous contact with the material, take a reading, pick it up into air, put it back down on the material. And you can leave it on the material for, a 5 count and pick it up for 1 or 2, put it back down. What that does, the Mentor constantly monitors the balance point of the probe in air. And that can be affected by the temperature of the probe as well as the temperature of the material. Again, our algorithms measure and compensate for all of that, but it's important to pick it up into air once in a while, let it find the balance point again, and go back down. And by doing that, you'll get your best accuracy over a very wide temperature range. So, one other thing, one other feature that's coming in this release of Mentor, in addition to the conductivity measurement, we've made a number of user interface improvements, some conveniences, calibration button on the bottom bar, some things like that. In addition to that, one of the most frequently requested enhancements was an indoor and outdoor mode. So we've added a feature in the settings, screen and display panel, where you can go to a bright mode. And that basically reverses all the colors, gives you a white background, black lines. This works for all the data views, all the menus. You can see menus are optimized with the black color on the white background. This makes a huge difference. Again, that's settings panel, screen and display, light and dark mode. Makes a huge difference for sunlight readability. So if you're working outdoors or in a very bright environment, another new feature with the conductivity release. All right, with that, again, I'm Dan Groninger, product engineer for the Mentor platform. Thank you for your time.